is presented by Professor Nader Engheta. And the title of this talk is 4D Structured Waves. Nader?
Okay, thank you very much, Mona, for a kind introduction. It's a pleasure for me to be here. I'd like to thank the organizer and chairs of the conference, Said Zohdi, Dorota Pollack, and Andrei Kudelsky, for the great effort in putting this virtual conference together and for the kind invitation to me to give this talk today. Let me share my screen. Okay, in this talk, as you can see from the title of my talk, I like to talk about some of the interesting aspects of four-dimensional metamaterial that can actually structure the waves. And by four-dimension, we mean that if in addition to the variation of material parameters in space, in X, Y, Z dimension, you also assume that your material parameters can change with time. How we can actually use this extra dimension in material parameters to structure the waves in order to have an interesting functionalities. Now, the concept of time-dependent platform for electromagnetics has a long history. Here, I've just mentioned, some of the names that goes back to 1950s that people have been very interested to look at some of the time-dependent systems. And this is a very active area of research these days with a renewed interest in bringing the dimension of time in material parameters as well. Before I show you an overview of some of the most recent results in my group, I would like to show you a few slides, about 4 or 5 slides of the background and the basic features of these temporal metamaterials. In my talks in four-dimensional metamaterials, I often like to show these 4 or 5 slides as a background in order to make sure that everybody in the audience will become familiar with some of the terminology, particularly in the context of temporal boundary conditions. So what is the analogy between spatial boundary condition and temporal boundary condition? Well, one of the most celebrated problem in electromagnetic boundary condition is Fresnel problem that we are all very familiar with that, and we teach that to our students. Is the simplest possible case of interface between two spatial media, in which case the permittivity jumps as a function of one axis going from left to right. And of course, we are all familiar with what would happen when the wave hits this boundary. What is the dual of that in the temporal domain? The dual of that in temporal domain is if you assume that you have an unbounded medium, homogeneous unbounded medium, and you have a wave propagating in this medium already, and at time t equal to t naught of your choice, you rapidly change the permittivity of the entire medium from one value to another. And that would be equivalent of the temporal boundary and analogous and dual of the spatial boundary. What kind of temporal boundary condition one can have? This is something that has been studied by many groups in the past. And indeed, just like what we do with the spatial boundary, we have to look at Maxwell's equations and look at the terms that involve the time derivative, and to make sure that the terms involving the time derivative stay finite. So what that means is that if you actually change the permittivity from one value epsilon1 to another value epsilon2 rapidly at a given time, you need to make sure that the vector d and vector b stay continuous just before the change and just after the change. That, as a result, implies that we would have this relationship between epsilon1 E1, epsilon2 E2, and same thing for magnetic field. I'd like to point out, but by the way, that this case is for the case of dispersionless material. As I will talk later on, if you introduce dispersion into the structure, this condition will change. We'll talk about it as we go through the talk. Now, as a consequence of that, what would happen is the relationship between the frequency and the wavelength in temporal metamaterial. Again, it's always good to compare it with what we know in the Fresnel, in the standard Fresnel problem. As you know, if in a standard Fresnel problem, you have a wave coming out with the frequency omega 1 and wave number k1, Obviously, when the wave gets refracted into the second medium, the two frequencies are the same for linear medium, but the wave numbers are not the same. Now, in the case of temporal metamaterial, the situation is different. If you have a wave with the frequency ω1 already in the medium, and then you change the permittivity from epsilon1 to epsilon2, then the wave numbers or the wavelengths stay the same and preserved, but as a result, the frequency will change from ω1 to ω2. This is something that in the plasma physics community known as photon accelerations. And what would happen, by the way, at this type of variation? Then what we need to do is to make sure that this condition that you see on the screen is satisfied just before the change and just after the change, which of course has another way of writing it as you see on the screen. Several groups, including Govind Agrawal group in the past, they actually calculated what happens to a monochromatic wave that's propagating in a medium with a frequency ω1, wave number k1. And when you do this rapid change of permittivity variation, you create two waves. One of them is a forward wave. The other one is a backward going. You notice that k1 stayed the same in these, but then omega now is ω2 over here. And of course, one of them is a forward going, the other one backward going. And several authors found out what would happen to the magnitude of this forward going and backward going, which according to Agrawal, that expression can be written like this. Now, in fact, this is kind of like a temporal dual of what we have in the Fresnel coefficients over here. I'd like to point out as we go through the talk is that often the backward wave is undesirable. But there are some cases that the backward wave could be useful as well, as we'll talk about as we go through this. So here I show you a simulation that my collaborator, Dr. Victor Pacheco-Peña, has provided for us. As you can see that here, the simple boundary between two spatial media, a wave packet is coming and you get the standard refracted wave and reflected wave. But if you do that for the temporal one, you will see what happens. A wave packet is coming, and at t equal to t naught, when you change the permittivity, you notice the forward wave and backward wave. And you notice, by the way, that the wavelength stay the same, but the velocity of propagation will change. And as a result, for the observer sitting at any point, the frequency of that wave will be different than we have there. Okay, so this was the background material that I would like to mention in order just to be familiar with the terminology. Now let's go to the what I want to present in the work that we are recently working on. What about the dispersion? What role the dispersion can play over here? And this is something that we have been studying, and you can find the detail of our work, theoretical work on these two papers, that one of them is going to come out in Photonics Research Archive and the other one in PRB. And also I'd like to point out that my friends, Professor Sergei Tretyakov and Roman Flory also have looked at other aspects of the dispersion of temporal medium. So we go to the basics. So what we write is we write vector D in this form, which is the most general way of writing this. And if we assume the Lorentzian dispersion that we often use, in material over here, then you can write the expression for the differential equation for the polarization vector P. And here we are assuming that the change that you would like to do in the medium happens in the number of the polarizable particle there. So in other words, you're changing omega p from certain value, let's say with the number density n minus before to a number density n plus after at t equal to 0. If you do that, we have to make sure that the wave number before the change and the wave number after the change stay the same, as I mentioned previously. Which means, again, we have to make sure that this condition is satisfied. But however, here, the big difference is this epsilon after itself is a function of frequency due to the dispersion. So this expression will have more than one solution that you will have for omega plus. And that's, of course, understandable, because if you look at the general variation of permittivity as a function of frequency, it's possible that you have more than one solution when you want to satisfy this equation. Let's take a look at, one example over here. Imagine we start with epsilon before the change being 1, and the frequency is omega negative. And imagine that you have a Lorentzian, but you assume for a moment that the loss is 0. And you assume that the resonant frequency of your material is 2 times of the operating frequency. Loss is 0. And what you'd like to have is to go from omega p 0 to omega p 3 omega minus, and that will give you the value of permittivity after the change at the frequency of omega negative with before. If you do that, you get this curve that you see over here. The vertical axis shows the ratio of wave number after versus wave number before, which you would like to stay at 1. And clearly you can see that you have two solutions to this expression. So here in this slide, I'm showing you actually the result, the temporal variation of the field inside this medium. Before the change, you have this single sinusoidal that you have with the frequency omega negative that I mentioned. But after the change, you notice what happened to the different quantities for electric field, magnetic field, vector D, polarization P, and the derivative of that. And you notice, by the way, that all of these, of course, continuous at t equal to 0 that we have over here. Clearly, you can see over here the presence of more than one frequency. And in fact, in this case, there are two frequencies that I showed you before. But this is because the resonant frequency of the medium in the dispersive case is not too different than the operating frequency. What would happen if you actually have a medium whose resonance frequency is far larger than your operating frequency? In that case, imagine something like this, that the resonant frequency is 10,000 times of the operating frequency. Then in that case, things go back to the case that I showed you in the introduction. In other words, in this case, you will see that the vector D stays continuous, but vector E and vector P has this jump. So indeed, the dispersion-less assumption is justifiable if we assume that the resonant frequency of the material is far larger than the operating frequency. But you may ask, wait a second, you told us that you will have two solutions for omega plus. How come? What happens to the second solution? You notice over here that before we have omega minus, and after that we have single frequency. So what happens to the second solution of that omega naught? It turns out that if you actually look at that, this second solution over here, which is this one, is going to go way, 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 way far in the very high frequency region. And when you do that, the value of permittivity at that very high frequency is very close to 0. And for that, if you introduce very small amount of loss, that second frequency essentially will give you no energy at all. This is the different amount of loss that you add over here. And you notice this is actually the same curve here, except the horizontal axis has been stretched to show you very, very small variation that's happening over here. So effectively, the system still continues, but in the time scale, it looks like there is this jump there. So everything is consistent, by the way, with the dispersionless assumption. So for the rest of my talk, I'm going to go back to the dispersionless assumption. And in here, we show how the dispersion will work. Okay, so in one of the analogy that we would like to make between the temporal structure and spatial structure is in the scattering. And that's what I call it, space scattering versus time scattering. What do I mean by space scattering? Well, conventional scattering is what I call space scattering. What do we mean by that? Well, we always deal with the scattering problem all the time. And what is that? Is that you have a medium, you have an unbounded medium, and certain region of space, the permittivity of that region is different than the rest of the space. And then when you have a monochromatic wave coming like this, and of course you get the scattered field, obviously with the same frequency, but different direction of propagation you have there. Now, this is the conventional scattering. Let's call it space scattering. Well, what is the time scattering? What is the equivalent of time scattering? Is it possible to assume this, that you have an unbounded medium, and this unbounded medium is uniform, and then you have a wave is propagating in this uniform medium, and then at certain t equal to t naught, you rapidly change the structure? What kind of scattering do we get there? Well, this is the work that my friend, Professor Matthew Fink and his group has done in the water wave. It's a beautiful work that he has shown that if you have a water tank and then you create some wave on top of it, if you rapidly move this water tank up and down, then you would get something in the form of a time reversal that you have there. And it shows beautifully that the original image is formed. We were very inspired by the work of Matthew Fink, and we said, okay, how can we bring this into electromagnetics? But this time, rather than having the entire region changes in time, we only change certain bounded region of that. So what would happen if you look at the temporal scattering in unbounded versus bounded space? So imagine the following. Imagine I have an unbounded medium, empty, and imagine I have a monochromatic wave is propagating through this. And now what I'm going to do, I'm going to look at a certain region of space over here, whose permittivity is still similar as the outside permittivity. But what I'm going to do is that while this wave is going, we're going to change the permittivity of that region from the background value to another value and bring it back down. What would happen to the wave there? And then not only one time we do that, but we want to do it several times, one after the other. This is the simulation that you can see what happens to that wave. So here we just showed the backward wave and the forward wave. You notice what happens when you do this one. It looks like that function kind of preserve the phase information and amplitude information of the wave on that object, on that bounded space. And you notice there's a backward wave coming and the forward wave going over here. And this is one of the cases that actually the backward wave becomes useful, because you can actually see if the size of the object is large compared to the wavelength, the backward and forward wave resembles or replicate the shape of the object and also the information about the incident wave. And what would happen? Can we take advantage of this? Well, it's very interesting that in Professor Fink's experiment, because he changed the entire water in one shot, then one change was enough. Here, because we are looking at the certain region of the space, not the entire region, and we only change this region in time, we need to actually repeat these changes. And when we repeat these changes, the backward wave has to come one after the other. Well, if it's come one after the other, how do we make sure that they stitch together? So that means we have to determine what is the period of this variation that we are making, which we call it capital T, and with respect to the size of this slab over here. These are related to each other. And if you actually choose that capital T properly, you notice that the backward wave, so the incident wave is coming like this, and this slab changes its permittivity from the background value to some value and coming back, just like what you see over here. And you see the backward wave, you can do it such that they stitch together. And if we can stitch together, can we use it for something? The answer is yes. We can have something that we can call it temporal slab lens or backward wave imaging of that. Again, let's go back to an unbounded medium. Imagine you choose certain region of space. It looks like this, which is the same material as outside. For now, it's just a mathematical boundary. And you have, you're changing this epsilon rapidly from the value to some value and bring it back. And as you see, you repeat that. And then you'll have a line source over here, which gives you cylindrical waves. So it's a 2D case over here. And when these cylindrical waves is coming into this, because of this rapid variation, the backward wave is going back and stitched together. So here, this is a simulation that my collaborator, Victor Pacheco Peña, has shown us, is that you see the wave coming over here. So this is the incident one, but this shows the total wave that we see over here. Now, in order to see the physics behind that, let me just here, we show you only the backward wave of that. If you remove the incident wave, you notice the backward wave is coming back and in a sense form an image of the original source that we had over here quite nicely. So essentially, it's kind of like a phase conjugation, kind of like that, in order to things bring it back. And this is very consistent with the Matisse-Fink's experiment in the water wave, but this would be only a finite region of space. That's what we call it, the temporal slab length. Here I show you the distribution of the field intensity that we have over here for the backward wave. And then we made our job a little bit more challenging. We said, okay, what would happen if we actually have the source within certain bunch of scatters that we have over here? Is it possible that the backward wave can actually go and basically undo the phase, if you will, and form the image there as well? And indeed, that is the case over here. As you can see, again, this is a total field distribution, and this is a backward wave that's coming. And you notice how it's going to undo the phase that we have there and actually focus at the point that the source used to be. Okay, now, so that's one interesting duality between space and time for the scattering case. But how about another case of duality? And that is, So far, we were changing the permittivity being a real value. In other words, positive real value, and we changed that real permittivity. What if we actually change the imaginary part of permittivity? In other words, what if we have a temporal variation of loss and gain? Here, I'm going to show you some of the results that we found in my group. I like to point out that my colleague, Professor Andrew Alou, and his group are looking at another set of aspects of these temporal variation of non-Hermitian scenarios, which are different aspects. Here, I'm showing what we found in my group. So the idea is the following. Imagine that you have an unbounded medium, and then you start changing the permittivity of this medium as a function of time with the period of delta T2 and delta T1. But this time, you're just changing the imaginary parts over here, and you keep the real parts the same. Now, in the past, we have shown that if we actually do this variation of permittivity in time, we can have a temporal effective medium theory that we developed in this publication. According to our temporal effective medium theory we have over here, if you actually assume that our epsilon1 is a complex number and epsilon2 is another complex number, but assuming that the real parts are the same, and we're just changing the imaginary part, what would happen to this expression of effective permittivity? Well, let's see what happens. If you put that expression over here, imagine for a moment, as an example, we choose epsilon real part of this to be 2, but the imaginary part, we are changing from minus 0.2 to plus 0.2. So this would be a gain and this would be a loss. And we go between these values. It turns out that if you use that formulation, and then you look at the real part of effective permittivity and imaginary part of effective permittivity, as a function of these two imaginary parts that we have over here, you get these two distribution, which is analytical results. Please note that if in this assumption, the real part of effective permittivity is only changing about 1%, whereas the imaginary part of effective permittivity changes significantly between here and there. Now, this is quite important because what happens is that means that actually the effective part, the real part of effective permittivity is almost stay the same. So if you look at the condition that we need to satisfy, which is K1 is equal to K2, and that means that omega-2 becomes a complex frequency. But if you plot this complex frequency, you notice that essentially the real part of that frequency almost stay the same, but the imaginary part of that frequency changes. This means that we don't have to worry about the dispersion over here. In other words, because the actual real part of frequency is not changing, we are essentially working at that real frequency, and it has the imaginary part that you will see the effect of that in the next slide. So imagine you start with a lossless medium. You have a wave propagating in this medium with the frequency omega-1, which is real, and the wave number K1, which is real. And then you start, putting loss and bring it back, putting loss and bring it back, like this. So imagine that you're changing the permittivity. Real part doesn't change, but the imaginary part, we have two examples over here. One of them changes from no loss to certain loss. The other one changes from no loss to a higher amount of loss. And what do we need to see? This is actually quite interesting, the result that you see over here. If you plot the result as a function of the space variable and time variable, clearly you see this is a single monochromatic wave is propagating. But when we do this temporal decay, you notice that there is an interesting temporal decay happens over here, and that's the imaginary part of frequency. But if you actually choose at any moment in time, if you look at the X variation, you notice that the K stays real over here. So that actually shows what would happen if you actually have a temporal variation of loss and gain. If you start with the lossy case, that actually gives you a richer system. Because if you start with the lossy case and you start changing the loss to the lower loss and even to a gain, then you notice that your system can actually have gain energy there because you're pumping energy into the system that we have there. So this is completely consistent with what we expect. Now, so up to now, what we were doing is that we are looking at the duality between space and time. Now, in Maxwellian electrodynamics, we know there's a lot of interesting symmetry and duality between space and time. But of course, there are also major differences between them. One, of course, in the time case, we have to make sure that causality holds true. And but at the same time, we know in the space case, in the Euclidean space, you have x, y, z, whereas time you only have one dimension. Is it possible, we ask ourselves, that we can actually increase the degrees of freedom in this temporal variation? So we said, okay, in that case, let's take advantage of electromagnetic parameters like permittivity and permeability, the fact that they can become anisotropic. So then we decided to look at this question, that instead of changing the permittivity in time from a single value in isotropic scenario to another single value, again, another isotropic scenario, what if we change the material from an isotropic case to an anisotropic case, in which case you can have two different permittivity values depending on the polarization of your wave. Now, if you do that, two interesting scenarios can happen. First of all, going back to the temporal boundary condition I mentioned, in that case, again, I'm assuming the dispersionless as justified by the fact that the frequency of the resonance is far larger than the frequency of operation. We have this expression. You notice that this expression, one of them, epsilon1 is scalar, but this one is a tensor. So what that means is not only you have a rapid variation of electric field, but also the orientation of electric vector can change. That has an interesting implication because it means that you can actually change the direction of the pointing vector in time. Another interesting aspect of that is that if you actually go from isotropic medium to anisotropic crystal in time, then you have to go from sphere of index to the ellipsoid of index. And you're all familiar with the wave propagation in crystals, that means that in every direction that we have to go, of course, the index of refraction is different. However, in the temporal variation, we have to make sure wave vector k stay the same in all directions. So in order to do that, that means in different direction, you will have different frequency of propagation. This is something that my friend, Professor Christoph Calo, has evolved and developed quite nicely, that he calls it inverse prism. So he has shown in his paper, which published in Optics Letters in 2018, he showed that if you do that in a crystal, he theoretically showed that in different directions you have a different frequency, even though you start with the monochromatic wave propagation, but it can change into a polychromatic wave depending on the angle of propagation that you have. In the case of change of the pointing vector, we decided to look at the dipole radiations in such structures. Now imagine that you have a dipole in a medium, and this is standard dipole and radiates in the donut shape. So imagine that I have a dipole that I put it over here and it's 45 degrees rotated. And if you look at the wave propagation, you see that standard wave, coming like a donut shape. This is a two-dimensional simulation, so it's a line dipole. But when the wave is coming from the antenna, if you change the background material from an isotropic to an anisotropic one, as I mentioned, the direction of pointing vector can change. So rather than having that donut shape that I was telling you about, the shape of the energy flow can change. So in this simulation, originally the dipole did like this, so you get this standard direction. But you notice as soon as you change that, the energy or the wave packet start going left to right, rather than going 45 and 135 degrees that you can see there. And of course, that means you can control the direction of energy flow in real time. So it's kind of like, ushering or guiding the energy packet to the direction you want. And that depends on parameter value of epsilon2, whether it's larger than this or smaller than this. Here I show you, you start with the same antenna, but depending how you change your epsilon1 to the other two numbers, either you can have a wave packet going from left to right, or it can go top to bottom. Now, when Victor and I were working on this problem, one of the interesting things that came out, kind of serendipitously, is that is it possible to have a dual scenario for Brewster angle, but this time for the temporal scenario? Now, remember I mentioned to you that when there is this temporal boundary condition, you get a forward wave, you get a backward wave. And sometimes backward wave is undesirable, sometimes it's desirable, like in the case of a temporal slab lens that I mentioned. But imagine that you don't want to have that backward wave. And what can we do? Now, we have the same scenario, by the way, in standard Fresnel problem, and you take advantage of Brewster's angle that is very well known. And we all know if you have a two dielectric region, non-magnetic, and you have a p-polarized wave coming like this, obviously it's very well known that at certain angle of incidence, the reflected wave is zero, known as the Brewster angle. So Victor and I ask ourselves this question: is it possible to have similar things for the temporal metamaterial? So in other words, can we have a temporal Brewster's angle? And the answer is yes, that's also possible. So if you have a wave propagating and then you change your parameter permittivity from an isotropic case to an anisotropic scenario, depending on the value of these anisotropic parameters, you can actually find a certain angle of your original wave such that the backward wave becomes zero. And indeed, when we go through the calculation, this would be the formulation, the analytical formulation that we derived from here. And you go through the analysis, and I don't want to bore you with the details of the mathematics, then you get to this expression, which shows that the angle at which you can actually have a zero backward wave radiation. And this depends, of course, on the original value of epsilon, that's the isotropic one, and you notice also the two elements of the anisotropic one. And if you plot the curves, you'll see the variation of that angle. Here, let me show you simulations that we have done. Here is the Gaussian beam that's coming and with the angle 15 degrees, which is not one of the temporal Brewster angles. And if you actually do rapidly change the permittivity from isotropic to anisotropic, you notice this Gaussian waves start going sideways. Remember, the direction of energy flow changes midstream, but you also see some backward wave is generated there. However, if you choose the angle of your Gaussian beam to be the angle that's given by that Brewster, temporal Brewster angle, you notice that you can essentially midstream change the direction of energy flow of your Gaussian beam, but the backward wave will be zero. And finally, I'd like to talk about this topic, and let's see how much time do I have, which we call it temporal deflection. Now, what do we mean by that? Imagine that you have a plane wave propagating in a medium, unbounded medium, and imagine you get a very certain region of this space, which is sub-wavelength, and the material of this is the same as outside, so there is no scattering over the wave coming like this. And imagine at t equal to t1, you would like to change the material of this in time and then bring it back at t2. But you would like to do this anisotropically, as I just mentioned previously, but this time, this variation in a very small region. If you do that, is it possible to actually change the direction of the photon flow, kind of like a deflect the photon temporally in time? So the idea is that if we actually create an anisotropic region over here, which in time changes like this, that you see over here. If in time, you have the original one and then you change it and then bring it back, is it possible that you can actually change the direction of the energy flow, deflect it to the direction you want? Please note that outside medium is not changing at all. This is unlike the previous slide I showed you. Outside medium is unchanged. Only very small region of this medium is changing over here. And if we can do that, can we actually determine what is the angle of deflection by design? And the answer is yes, you can do that. So here, based on the formulation that I showed you, here we are showing what would happen if the angle of incidence that you have is 25 degrees. And then you choose these two values, the after change that happens. And this plot is show you what should be the angle of the scattered wave or the deflection angle that you have there. So let me show you some simulations that we have at this point. But it's a two-dimensional simulations. And imagine the original wave that's coming in an unbounded medium comes with the angle 25 degrees. And in this region, you're going to change that. And you choose, the values that you have over here. Let's say one of these values. This is epsilon to R2z is 8, epsilon to x is 1. So this would be, for example, one of these curve that you see there. See? And you notice what happened. The scattered wave goes in the angle around 80 degrees. The original photon wave that's coming was 25 degrees, but this actually deflected to the direction you want. Again, outside medium is unchanged, it's just fixed. And then if you wait long enough, you see what happens to that. The scattered wave is getting away. And by the way, because you're bringing it back, then there's no scattering anymore. So only in that very short period of time, you create this deflection in the direction you want, even though the size of the structure is small compared to the wavelength. And you notice as you wait, what happens to the wave that goes through. Now, let's choose another number over here. For example, this is the other one. Again, the incident wave is coming at 25 degrees, but depending the choice that you have for the anisotropic one, you can deflect it in different angle you want. And the other one was 80 degrees, and this one was 5 degrees. This can provide an interesting possibilities, for example, for asymmetric or some called non-reciprocal scenarios we have there. So imagine that I showed you that two-dimensional simulation again. In this case, the incident wave is coming with the angle θ1. And then you do this change that you see over here, and that is deflected in the certain angle θ2. But now let's ask ourselves this question. Let's repeat this scenario again. But this time, the incident wave comes in the angle θ2. When you do the same temporal change, are you going to get the deflection back to this? The answer is actually not necessarily. And that, of course, makes sense because this is a temporally varying system that we have over here. And so this can create an interesting possibility with some degrees of freedom that you can play with. Here, we show you different results that we have there for these cases that we can see. That brings me to the end of my talk. I like to thank those members of my group who have contributed to different aspects of the work that we currently have in my group in the area of four-dimensional metamaterials. In particular, I'd like to thank, Victor Pacheco Peña, who is the result that I was showing mostly today is the collaborative work that he and I are doing together. And so in summary, structuring the waves using the 4D structure can give you a richer platform to do interesting scenarios. Obviously, there are challenges with regard to some of these variations that we have in time, but that can give rise to interesting set of possibilities to see how we can actually control photons in a different way that we would like to do that. Before I end, I would like to bring to your attention that Victor also has 2 talks in this symposium. One of them was earlier today, and the other one is tomorrow in different aspects of this temporal metamaterial. And I'd be happy to answer any question you have. Thank you all very much.
Thank you very much, Nader, for the excellent and very insightful presentation. We have a number of questions in the Q&A section. I'll read them. The first question is asking, your concept assumes that epsilon switches in time similarly fast as the carrier wave. There is no way to provide electronic switching speed, for example, up to 500 terahertz. So you have to induce this kind of epsilon switching in another optical way. But this is well known as chi-3 nonlinear optics with all the well-known effects such as frequency conversion, etc. What is the difference of your concept to ordinary nonlinear optics?
Okay, thank you. Thank you, Thomas, for the question. First of all, how fast you need to change the permittivity, that depends on what application you have in mind. If you want to actually keep the temporal boundary the way you have, then the rise time or the fall time of the variation of permittivity, as you said, should be short compared to the period of your signal. However, if the goal is to do the frequency variation or frequency conversion, as long as, and this is very important, by the way, as long as your wave stays in the medium during the variation of your permittivity, that frequency conversion can still happen. Now, the magnitude of the backward wave and the magnitude of the forward wave will become different naturally. But as long as your wave stays within your medium, while you're changing your permittivity, then that conversion can happen. So one scenario you can think about is to actually have a wave in the ring resonators. Obviously, we don't have infinitely long material, but if you actually have your wave in the ring resonator, and then you change the permittivity of the ring, then that variation of permittivity doesn't have to be fast. Now, however, your point is well taken that some of these concepts that we were working on perhaps is more suitable for the lower frequencies, like in microwave and so on, in which case the switching time can be small compared to the microwave frequency or microwave period that you have there. Now, nonlinear optics can be useful in generating these changes. And in fact, Professor Bob Boyd was showing, yesterday in his talk, or I think it was yesterday, in his talk about, how using the giant nonlinearity of E and Z, you can actually have the wavelength conversion that you have there. But some of these concepts that we are looking at doesn't have to be necessarily an optics system. Obviously, we all would like to go in the optics, but some of these could be quite useful in the microwave scenarios as well. So there are big differences between these and now nonlinear optics can be used as a tool to generate this change of permittivity. But there are different aspects that these four-dimensional metamaterial can introduce that in the nonlinear optics is not there.
Thank you very much, Nader. I think you answered the next question, which is also asking about how fast the index change should happen. I'll go to the third question. Wonderful talk. Could you please give an example of a material or compound that can be used as a temporal metamaterial? And do you have also in mind a nano device exploiting these temporal material properties?
Well, thank you, Luca. By the way, thanks, Dimitri Chigrin, for your question as well. Luca, yes, one interesting point you can consider with regard to temporal material. As I mentioned, for example, large nonlinear material can be an interesting platform for this. As I mentioned, Professor Bob Boyd mentioned in his talk with regard to ITO and giant nonlinearity in E and Z material. But if we come back to the lower frequency, like in microwave and even in the RF frequency in electronics, variation of parameters in electronics have been done, with the varactor and with a lot of, tunable and time varying circuit elements that can be done there. Nevertheless, I mean, there are different aspects that can be still come into the semiconductor aspects, how you can actually rapidly change the electron density of a system in order to change the permittivity change. Although there, the change in the permittivity may not be as much as one would desire. So I would say some of these properties could be useful in the lower frequencies. Some of them can be envisioned when we go to the higher frequency as well with the high nonlinearity. Anyway, there are different considerations that we are looking at. As I mentioned, sometimes the proof of concept experiment is always, not always, but most of the time starts from the lower frequency to see some of this. Let me see, did I answer all of it? Do you have also in mind a nano device exploring this temporal? Yes, I mean, conceptually, some of the topic that I talk about could be applicable into nano devices. For example, this last topic I mentioned with regard to temporal deflection, one can imagine that you can actually have a very small, a sub-wavelength particle that you can actually change that with the nonlinearity and with the proper nonlinearity and anisotropy in order to create this. And so again, some of these concepts, in fact, Harry Atwater in his talk was talking about how fast you can actually change the system in metasurfaces. Those changing in time on metasurfaces could be useful in developing some of these concepts.
Thank you very much. We are really running out of time, but I would like to get to all questions. This is the last question. Great talk. Thank you very much. Could temporal slabs be used for detection applications?
We hope so, by the way. That's one of the reasons that we are interested in, one of the reasons we are interested in that, because it's something that essentially you can think about as a lens on demand. In other words, the lens is not there, but when you actually change the material within that range, you can actually create the temporal lens. So I'm hopeful that could be something to be considered. But there are other applications we have in mind as well.
Well, thank you very much, Nader, for again the excellent and insightful presentation. So this concludes our plenary session. I would like to thank both of our speakers for their excellent talks, and I hope you enjoy the rest of the conference. Thank you.
Thank you, Mona. Thank you very much.